So in this video, we would like to look at the new concept, which is called the null space of a matrix M. It is defined to be the solution space of the homogeneous linear system with the coefficient matrix, the same as the matrix we look at. And let's look at an example now. So please try to describe the null space of the current matrix M. And it basically means you have to set up the homogeneous linear system by using the matrix form, and you have to solve it now. And let's look at all the solutions to this matrix form. And by the Gaussian elimination, I think we can do row 2 minus 2 times row 1. In that case, the second row will be completely 0. And please recall, for any homogeneous system, it has at least one solution, which is the 0 solution. It means you can set up all the variables to be 0 to get at least one solution. So for such a homogeneous system, it can be either having exactly one solution, which is the 0 solution, or it can have actually infinitely many solutions, right? I think this case actually have infinitely many solutions because the row 2 now is 0 equals 0, which has no information for us to solve the system. Now the system means it has only one equation, but you have two unknowns, right? And it belongs to the case of infinitely many solutions. And let's try to write down all the solutions by the parametric form. Because you have only one equation and things can be easy, we can set the parameter t be the last variable y. And let's write down x in terms of t now. So it basically means x can be written as minus 3t, right? So when you look at the solution vector, it basically means I can write the solution as a column vector like this, and x is minus 3t and y is t. It means the solution actually looks like this. And please recall t is any real value, right? So it means what? What is the dimension of this space? Can you tell me? So it means that this null space of M is actually a one-dimensional space in R2 because of the fact that now the vector has two coordinates, right? We can call it R2. And this one-dimensional space is basically a straight line governed by the direction of this column vector. So let me put it here. The null space can be written as the span of this one single vector is basically a straight line along the R2. And that's the answer to this problem. If you're asked to write the null space is a one-dimensional space spanned by just one single vector because we have only one parameter, right? So it gives you a sense that it must be a one-dimensional space when you use only one free variable to generate all the solutions. And let's look at other examples. So please look at the current matrix M. Can you write down the null space here? And I think there's nothing to do in terms of the row operations because it's already in the upper triangular form. So to write down the null space, you have to set up the linear system like this, which means I can look at this directly. And let's try to solve this system. The second equation is clear. For y equals 0 means the second variable must be 0. And for the first equation, because y is 0, it basically means x must be 0, right? So that's the case for the exactly one solution for such a homogeneous system. It means the solution, the only one, is the 0 solution like this. And 0 solution means what? It means it's only one single point on the R2 space. It is in the R2 because there are two coordinates you look at for each column now, right? Because there's only one single point on the R2 space for the solution vector. It means it's basically a zero-dimensional subspace in R2, and that's basically our null space now. The null space of M basically contains only the 0 vector because of the fact that our current linear system has exactly one solution, which is the 0 solution now. And let's look at another example. So please look at the current 3 by 3 matrix now. And if I'm asking you to find the null space, can you see how to do that? Basically, you're asked to solve this linear system, and I think row 2 minus 4 times row 1 will actually make the row 2 0. And similarly, for row 3, you can use row 3 minus 2 times row 1. Then it would be a 0 row also. So basically, the last two rows are something like that, and you are having only one non-zero rows, which is the first one. Basically, now it's a one equation, three unknown system, right? So it means what? It means this system automatically has infinitely many solutions. Can you describe all the solutions now? So because we are left with only one equation, things should be quite easy. For example, you can set the last variable to be t. But I think it's not enough because you still have two unknowns remaining after setting it to be t, right? So I think we have to use one more parameter to describe the solutions, I can make the second last variable y to be s, and in that case x can be written as something in terms of s and t, right? So I can make x plus 2s plus 3t to be 0. It means x is basically minus 2s plus 3t. And can you write all the solutions down now? Basically, all the solutions can be written as this way. You see, and st are free variables. It gives you a sense that the solution space actually has 2 degrees of freedom, in the sense that it should be a 2-dimensional subspace in R3. It is in R3 because there are actually 3 coordinates in each vector, right? And that's the null space of the matrix M, right? And if you try to write it in a more careful manner, you can look at the solutions again, because I can split the 2 variables st to be something like that. If you split it, I think what you're getting is something like this. It's minus 2, 1, 0 for the first vector attached to the first variable s. And for the second vector, it's going to be 3, 0, 1. If you don't see what I'm doing, I'm basically trying to separating the variable. For example, I can separate it like this, and then you automatically get what we have here. So basically, it means that our current null space, we can have the basis vector, which is the first one like this, and the second one is 3, 0, 1. I'm just using these 2 vectors as the basis vector of the 2-dimensional subspace of the null space of M here. And that's the end of this video.